Yeah, like that was last year. Yeah, okay.
It's hard to like you don't know how to.
Okay, guys, page 20, page 20.
But that's so good. You get what?
Should I get a card for being the
No, but yeah. Yeah, Adam is so smart. Yeah.
All right.
It's actually
Page
that
20.
you used it for that.
We have two more sections to go over. This technically falls under the differential equation unit, but I pulled it out. This is a easy topic, so I want to just save it to now to present it. These different equations are a little messy, but we don't have to worry about solving for it. Just to be able to know how to interpret it for these kind of specific cases. So logistic model. Okay, so logistic population growth is when the growth rate increases quickly at first, but then slows as the population reaches carrying capacity or limiting value. We're gonna see this L variable show up. So the L variable represents the limiting value. It represents the carrying capacity. So the graph for your logistic equation or your logistic differential equation will look like this, where your growth rate is increasing at a fast rate, but then eventually it's going to slow down. It's still going to be growing, but it's going to be kind of hovering near that limiting value or that carrying capacity once it reaches a certain point. So population will continually increase, but the growth rate is changing. The growth rate is slowing down. So your initially your growth rate is increasing. You can tell by the fact that it's concave up, right? Your rate of change is increasing. Here, the slope is still positive, but it's concave down. So my growth is increasing, but my growth rate is decreasing. Or the population is increasing, but the growth rate is decreasing. And this is visually, this is the inflection point, right, where concavity changes from concave up to concave down, or vice versa. But for our case, it'll always be from concave to concave down. Your inflection point, it's going to be where your max growth rate occurs. Okay. And your max growth rate is always going to have a y value of your limiting capacity or your limiting value divided by 2. A real world application could be with animals and how many the land can support. If there is a limit of natural resources, then that's going to dictate how much the population can max out at. Okay, so we have two variations for logistic differential equation. The derivative of a logistic equation is typically written in one of the following forms. But the ones that I think we're going to use more is going to be that first one here. Okay, so dy dt equals ky times 1 minus y over L.
Is this the CE to the KT? Or?
That's exponential growth. It may bear some relationship, but but that is an equation where we actually have an equation. This one, we could solve it, but it's such a long process, we're not gonna worry about it. So a lot of times our differential equation is gonna live in the derivative form. We're not gonna solve it. At least the problems that we see are not gonna involve solving it. It's gonna involve at the derivative level. So dy dt indicates your rate of growth. Your dependent variable y, because my independent variable is time. So as time passes, my dependent variable y shows up twice in the differential equation, which indicates the likelihood of logistic form. So when you see y show up twice within your print or within your differential equation, that's usually an indication or a kind of a hint that you're looking at a logistic differential equation. And then you kind of switch gears in terms of, oh, okay, this is how they want us to, how they want me to move forward, is to treat it like a logistic equation. In either form, K and L are positive constants, and L is the limiting value. So we're gonna, a lot of problems are asking you what the limiting value is, and we can pull it easily if we can get into this form. And the problems that we do, I think that AP exams are typically using this first form. Okay, anybody still need the notes here? All right, so let's look at these examples here. Identify the limiting value and the y value of the point of inflection for each solution of the differential equation. So we have dy dt equals 6y times 1 minus y over 3. So this one matches nicely with this first form. We see that 1 here, we see the variable y with the coefficient, and we see y over 3. What's the limiting value? 3, yep. So this graph is going to get closer and closer towards 3. It's going to flatten around 3. And then what's the y value of the point of inflection? Yeah, so whatever that inflection point is at some t value, it's always going to be your limiting or carrying capacity divided by 2. That's going to be the point where the max growth rate is going to occur. Yeah, so 3 over 2. Number 2 here, this is in a different form, but we can also pull the limiting value that's in this form. What's the limiting value there? 16, yeah, got the y there. You don't necessarily have a fraction in front, but we have the y, we have the L minus y here. And the y value of the point of inflection. Is
that the second formula is the L in the denominator the same as the one within the parentheses?
yes, but the 2 is a reduced expression, so we don't have to worry about what the K value is.
32.
Right. So these two things will answer most questions you will see on the AP exams for logistics. The maximum value of the logistic function is limiting value. So a lot of times problems are asking for that limiting value. And the maximum rate happens when y double prime, when your second derivative changes from positive to negative. And that's where that point of inflection occurs. That's where that max growth rate occurs. Okay, let's try 3 and 4. And number 3 looks like the first formula there. So to answer the question that you guys were asking before about we can solve this differential equation and it will look something like this. We don't really have to worry about this too much. There's not, I haven't seen any problems that really uses this, but just for, we can derive it, and this is the actual solution of this differential equation. So that's just for you to keep in mind, but don't have to worry too much about it. And let's skip 5 for now. It's a little bit more involved than what I think we need to be able to do. So let's go to number 6. Now, sometimes we want to be able to match the differential equation, but it's not quite in the form that we need it in. We need to set that set of parentheses up, and usually it's easier to target that first equation. So that's what we're going to try to do. If we can get it in the form of this equation, then we're able to gather the data that we want. So we're going to try to get in this form here. What can we do to get this right side to begin to look more like that factor? What can I factor?
1/5 y.
Or that 4/5 y, right? We want that first term to be 1, so we want to pull everything out from that first term so that a 1 can remain.
Okay.
So let's try that. Okay, what can we do if we factor a 4/5 out of so basically we have to do 1/50th divided by 4/5, right? Sorry, 1/50th divided by 4/5. So that's the same thing as 1 over 150 times 5 over 4. Double check this, right? 4/5 times 1 over 120. It does give us 1 over 150. So we did factor this out correctly. Okay, what's the L value? What's the carrying capacity? Yeah. Okay, number one. Population changes at a rate modeled by the logistic differential equation, dy dt equals 0.3 y times 4,000 minus y, where t is measured in years. What are all the values of y for which the population is increasing? So population increasing simply means where y prime or dy dt is greater than 0 at a decreasing rate. So this is where what is that referring to?
Oh, secondary.
Yeah, second derivative is negative. Right, so we're looking to see where is y prime positive and y double prime negative. So let's start off with dy dt. Let me clean this up to get it myself ready to get to the second derivative. I'm going to distribute the 0.3y through so I can just rely on power rule and not have to go through product rule there. So I'll multiply the 0.3y through. Yes, yeah, you get the calculator. Okay, it makes it easier for me to find the derivative. Remember, as we find the derivative, we're finding the derivative with respect to time here. So dy dt becomes d2y over dt2. That's the second derivative. 1200y becomes what? Remember, time is independent variable, so y becomes dy dt. So it kind of has that related race feel to it. 0.3 times y squared becomes you factor out the dy dt and set equal to 0. Because I'm just creating a second derivative sine line so I can figure out, test my second derivative sine line to see where is y double prime is less than 0. I can factor out dy dt.
So if the variable, if the derivative was t, then you wouldn't have to do the parentheses, right?
Right, exactly. Right. But with these, that's just the equations, it's always going to be in terms of y. Okay, so we can ignore that dy dt. We just have to figure out where is that 1200 minus 0.6y is equal to 0. So we know that there is a critical point at 1200 here. I plug in a value anywhere between 0 and I'm sorry, not 1200, 2000 divided. I didn't solve for y here. Okay, any value that I plug in, that is less than 2,000, I'm going to get a positive value out of it. Anything that is greater than 2,000, I'm getting a negative value out of it. Now, y prime also has, if we look at y prime here, we know that y prime is going to be positive everywhere from 0 to 4,000, right? Anything more than 4,000 is going to be where my dy dt is going to start become negative. So I can just say from 0 to 4,000, my entire y prime is positive. So I want to know where my population is increasing. So I know I'm looking at that interval from 0 to 4,000. But more detail is we want decreasing rate. So decreasing rate will be from 2,000 to 4,000. So this will be where both match up. We want a decreasing rate with a positive population increase. Mhm. That's true. That's true. Right. Because of the fact that it's a logistic equation, we know that L over 2 is 2,000 and everything above is rising. Yep, we could do that as well. I want to show you this method for us to do this from a curve sketching standpoint. But I think that's also a good point too. Did not see that. Mhm. Um, yeah, we are ignoring it, but I think it's just a good habit for us to do the derivative with respect to time here. Yeah. Okay, I want to skip number 2 here, and let's begin to look at some of the multiple choice or the questions that feel more similar to AP problems and the ones that you're going to see. So page 23. Okay, population P of a city at time T is increasing according to a logistic differential equation. Which of the following could be the differential equation? So we want to find one that kind of has the look that we are that we are seeking. Which one has the features that we're looking for to make it a logistic differential equation? Yeah, so B, we need this to be a dependent variable. So it's just going to be what? Just E. Yeah, time is the independent variable. We need that. We need that Y, that dependent variable, showing up twice. Okay. Number 4, the total number of positive COVID cases in the city. T days after the start of an outbreak is modeled by the function y equals C of t. That is the solution to a differential equation, dy dt equals 1 over 7,000 y, 1,600 minus y. It kind of fits that second differential equation model better. If there are 10 reported positive cases initially, what is the limiting value? So we're looking for that L value for the total number of positive cases. What's our carrying capacity or our L value? Yep. Yep, that's it.
It's just like.
Yeah, it doesn't mean anything for this problem. It's kind of we don't need it for this problem. Yeah. Yeah, I mean, it's asking for a limiting value, so it doesn't matter where we start. Right? Let me skip 5 for now. Come back to that. Let's go to page 24. Okay, the rate of change dPdt of the number of people in the mall is modeled by a logistic differential equation. The maximum number of people allowed in the mall is 2,000. At 10 a.m., the number of people in the mall is 200 and increasing at a rate of 400 people per hour. Which of the following differential equation describes this situation? All right, let's gather some information here. What can we assign the 2,000 to be? L. Okay. So at 10 a.m., the number of people in the mall is 200. So that's what? P, right? When P is 200, the rate and increasing at a rate of 400 people per hour. What variable is that? dP over dt, right? People per hour, that's rate of change of people. Okay, so really we're just trying to solve for K, right? If we can solve for K, then we should be able to match with one of these options. Right? Yeah, A and B will be gone. You know, we're dealing with between C and D. I'm gonna match it up with the second one here. So if I insert 400 in for dPdt, L and 2000 in for L, and then replace P with 200, I can solve for K. Once I solve for K, then I should be able to match my choice there, right? K over L is the same thing as K times 1 over L, so I can avoid complex fraction. Okay, number 7. the population P of a deer in a preserve grows at a rate that is jointly proportional. So we know it's gonna be the product of two things here. To the size of the deer population and the difference between the deer population and carrying capacity. So we know population of deer, that's growth rate, that's dPdt, is jointly proportional to the size times difference between deer population and carrying capacity. So P minus L. So that's looking more like this last form, right? So we know that this S is just going to represent that's K over L times Y. Or times P. That's my bad, not P minus L, L minus P, since we're doing.
Why did you put in?
Oh, S to represent the size. It says the size of the deer population, so I just put the S in place of it, but I knew that was going to fit more like this one here.
Is it the size of the deer population, same thing as the deer population, or?
Right, the size of the deer population is going to, it's got to fit into this form, so we put that K over L as P. Okay, we know the population is 3,000, so that's our P. I'm sorry, carrying capacity is 3,000, my bad, that's not P, that's L. Okay, so we're trying to make this look like one of these options here. If I multiply through by 1 over 3,000, then that should make it look like that, right? Okay, try number 8. So we're taking all this data, see if we can solve for K. And once we solve for K, then find the equation that matches. oops, 1/8,000. Okay, number 9. The limit as t approaches infinity of p of t, that just represents your limiting capacity. So number 9 is just asking for the L value. All right, limiting value. Carrying capacity. Finish off with 10 and 11. Okay, number 10, we're looking for the false statement. Carrying capacity is 1,700, that's true. Part C is also true, as you know, the max rate will occur when population is the carrying capacity divided by 2, which is 850. And then to the right of 850, We know our, logistic equation will look like this. So we're expecting after 850, the slope is positive, but the cavity is negative. B is gonna be the one that's false. That doesn't fit that L over 2. Okay, number 11, we know our carrying capacity is 400. We can take that 400, put it in for L. We can also distribute the K through. And based off of our answer choices, we know that K is 0.1, since that's consistent across all the equations. And then we can narrow down which one must be. Start here, place K with a 1, and then once we get into this form here, we know that it's really just figuring out which one of these to choose. And you know, 0.1 divided by 400 is 0.00025. So it's going to be on top of answer choice A.
Are you supposed to know like which one of the formulas you're supposed to use? Like why can't you use the KP parentheses 1 minus
Because our answer choices fits this a little better, right? If I distribute this through, I get b minus b squared. So I'm looking at my answer choices to kind of decide what is a better starting point for me. I think. Okay, check your calendar for your homework, and we have one more section to do, and then we can start our quiz review on Thursday. Okay, okay, your thoughts.
Yeah, I think it's like what it is, but you know, it's only good stuff. And some sort of you'll see based on the logical. Assume that sense that I think that's what my problem. So that's like I'm going to do this. Like,
I think we can skip that for now. Yeah, don't worry about it. So I don't think what you're saying. I'll never do it. Go to the answer key, but yes. We might have improved. Oh, yes. Wait. This thing will say hate. Oh, we have research.
It's not the that was distributed to 1.2, that's unfortunate because it's the same proportion of the 3 times. Because like
Oh, and what?
so I didn't know that. I saw like reminder of the things that what you said. I said that it would be able to be both terms so the proportion.
Oh my gosh. You said don't go on.
I get punished.
So if you get out, and then there's
Your mom.